All right, take a look at the warm-up. Hopefully you had a chance to get started here. Once again, I can zip through these calculations here, but real value is when you get started on them, you see where you get stuck. I really encourage you to start these as soon as you can. All right, so what am I going to do? First thing I'm going to do is I'm going to turn it into a matrix equation. If I let u equal the vector u1, u2, then this system looks like u prime is equal to my coefficient matrix times u. So now I want to solve the system. I got to find the eigenvalues, eigenvectors of my matrix, and then form my solutions. And we know that because we assumed that my solutions are going to look like some vector e to the lambda t. So I got to find the eigenvalues, I got to find the eigenvectors, I can then find my individual solutions, and I can form my general solution. All right, calculate my eigenvalues. I take the determinant of a minus lambda I equals 0. So I'm subtracting lambda off the diagonals, which is 1 minus lambda squared minus 4. Expand that out a little bit. I got 1 minus 2 lambda plus lambda squared minus 4. I reorganize. Then I factor. And then I say, when is this thing equal to 0? When lambda is equal to 3 and negative 1. All right. I need to try to do as many of these problems as possible so that you can do it about that speed. That's the speed with which you should write out this process, right? Subtract lambda diagonals, write out the polynomial, do the factoring. If you don't see the factoring, it could take a little longer. You do the quadratic formula, but that's the big idea. All right, so now I have my eigenvalues. Next thing I have to do is find my eigenvectors. So now I am solving a minus lambda I times my eigenvector equals 0 for the different eigenvalues. So if lambda is equal to 3, for instance, then I'm solving a minus lambda I, so that would be subtracting 3 on the diagonals. I get minus 2 and 4, 1 and minus 2. This thing times whatever that vector is that I'm trying to figure out, 0, 0. Do not have to write out that linear system, right? Because we're trying to find out what x1 and x2 are. So the next thing I would do is just write the augmented matrix and reduce it. So you don't necessarily have to write out the whole system. You could certainly just jump to this guy and row reduce it. Now, do I even need to row reduce it? Not really, right? Because I know that there has to be non-zero values of x. That's what I'm looking for. I've chosen lambda specifically to give me non-zero vectors of x, which means these two rows have to be multiples of each other. That's what has to happen. Now, why do I always row reduce it? It's really a check for me to make sure I haven't screwed up my eigenvalues. Okay? So I'll row reduce it real quick. I will divide the first row by negative 2. I'll get 1 and negative 2. And then I'll just get rid of the second row there. Okay, I feel better. I did the eigenvalues correctly. It's really just a check for myself, though. Okay. All right, now I'll rewrite this in terms of the equations. That first row is associated with the equation x1 minus 2x2 equals 0. If I want, I could solve that for x1 to make it a little bit easier. But the idea is my eigenvector is basically a set of x1 and x2s that makes this thing true, right? And the idea is any multiple of that guy will also be an associated eigenvector. So for instance, I could say if x2 was 1, x1 would have to be what? 2. There is an eigenvector. You certainly could have said if x2 is 4, let's say if x2 is a half, x1 will be what? 1. Also an eigenvector. Also perfectly correct. You can throw that in your solution, you'll be all set. However, if I have to do stuff with this later, I probably don't want to carry that half around. So if both of these will work, use the one with integers. Right? It's totally up to you what you choose to put in there. Okay? But they all should end up being multiples of each other. So that's how I can tell if you're right or not, depending on your choice. It better be a multiple of what I chose. Okay? Questions so far? All right, just a reminder, put all phones away, off of desks. Behind you over here, okay. Yeah, put your phone away, please. Thank you. All right. Okay, so that's eigenvector. We found one eigenvector, right? So we have one eigenvector, one eigenvalue. One solution is going to look like 2, 1, e to the 3t, and we're all set, right? One solution. Now we got to find the other solution. Now we say if lambda is equal to -1, we do the same thing. We plug this guy in. You got to be careful, right? We're subtracting a negative, so make sure you do that correctly here. I have 1 minus a negative, 1 is 2. I got 4, 1, and 2 again here. Once again, I could row reduce it if I want just to check. I would row reduce it and get this thing, kind of to verify that my eigenvalues are correct. That equation that I'm getting at is x1 plus 2x2 equals 0. If I want, I can solve it for x1. If I don't want to, I don't have to. This eigenvector could be what? Well, if x2 is 1, x1 is going to be what? -2. There's my other eigenvector. That means my second solution should look like -2, 1, e to the -t. And then lastly, my general solution should be some constant times the first solution plus some constant times the second solution. All right. Any questions? Yep.
Can you show U1, U2 solutions and then go to the overall solution in general?
Say that again?
Do you have to show both U1, U2 and the general?
No, not necessarily. You can just go right from the eigenvalues, eigenvectors to your general solution. That's totally fine. You don't have to specifically write out that guy or that guy. That's fine. But I got to see this guy. Other questions? Yep. Yep, the eigenvector. Sort of. I mean, depends what you mean by eigenvectors. The eigenvectors are 2, 1, right? Those are constant. Any derivative solution, right? This vector right here, there's a 3t in there. Right? So the vector is really the product of those two guys there. But yeah, you can essentially 2, 1 like constant vector. The derivative is either 3t or 3. All right. All right, so that's the warm up here. The big idea is we have this general solution process. And the idea is we get our system. We're assuming a solution looks like that vector e to the lambda t. So we got to find the eigenvalues. We got to find the eigenvectors. And then we form our solutions from there. Just that big picture, take a step back. What are we really doing here? This is what we're doing. And one of the things to note here is those eigenvalues of A. To find those, we're basically solving a polynomial in lambda. And so when we find the roots of that polynomial, so far we've been pretty nice. We found nice distinct roots. But of course, in general, those roots could be complex. Those roots can be repeated. So we also have to talk about how we form solutions now with those other kind of roots. And so that's really the topic for today. All right. So polynomials could have these other cases. What do we do with those guys? General plan for today is to introduce that stuff, do a quick check with Mathematica. We probably won't get to the end. In fact, we probably won't get to the repeated root case. Now, first class had some questions about some of the homework. I believe I got some questions here as well. So the two big questions are, one, how to deal with 3x3 things, right? Because we need a little review of linear algebra there, but also how to deal with that initial condition guy from that other homework question. So let me make a little space here and go through those two pieces. All right. So in one of the questions, you had some sort of, and this is probably not the real question, I'm just kind of writing in values here. You had some higher order linear differential equation with constant coefficients. You had to convert this guy into a system. So you let u1 equal x, you let u2 equal x prime, did a bunch of stuff, right? And you generated a system. Okay. And then you went ahead and found the eigenvalues and eigenvectors of the system, and you formed your solution. And you had some sort of solution that probably looked like C1 eigenvector e to the, I'm making numbers up here, some value like that. C2, some values here, e to the 14t. Sure, it wasn't 14, so. Okay. But it looks something like this, right? And throw in some pretend values here, whatever. Okay. You form some solution that looked like this. And the last part was to use your initial condition to find the values of C1 and C2. Okay. Well, if we were just dealing with this problem, we were given conditions that looked like x of 0 equals 1, whatever it was. X prime of 0 is equal to 2, whatever that was. Okay. If we wanted to have an initial condition for this system, it would look something like this. Here would be an example of an initial condition. And what this really means is, remember our vector u is just a vector containing those little functions of t that were in our equations. So our initial condition is really just a vector. We're evaluating those little functions at 0. But in this specific case, because this came from converting over that higher order linear system, well, u1 is really just x. And u2 is really x prime. And we were really given those values of 1 and of 2 up here. Well, this is kind of the process we go from converting the initial conditions in the high order case, and we can kind of convert them now into the initial condition for the system. Okay? Here's the value of u1 and u2 at time equals 7. And then how do we actually apply the condition? Here's my solution. And all I'm saying is, what is u? U is 1, 2 apparently, when t is 0. And so e to the 0 is just 1. E to the 0 is just 1. And you can solve this however you want, right? You can expand it in two equations and add or subtract equations. You could rewrite it in matrix form. Any follow-up questions here? All right, and then we got some linear algebra review. Well, what do we do about 3x3 systems? All right, I have a 3x3 system. I'm going to make up some pretend numbers here. The idea is at some point you have to calculate the determinant of a 3x3. And this can be challenging here. Challenging for two reasons. One, some of you might have gotten sucked into the, I'm going to do like an I, a J, a K, and then an I and a J or some weird thing and then something like that to calculate these things, right? And that's great in Calc 3, where you're really just doing 3 by 3 things. Everything's kind of nice. You don't have a choice about what you want to do it because there's usually actually an IJK in the top. But now when we're doing more general linear algebra, that does not extend to 4 by 4 systems or larger systems. It also doesn't necessarily take the easiest path through the problem. Okay? So in general, how you actually calculate the determinant is bigger than 2 is you break it down into smaller 2 by 2 pieces. So we know how to do this, that determinant. All right, we take this product, A times D, minus that product, B times C. For a bigger one, we have to expand down a row or a column. So I'm going to expand along my first row. To do that, I take the first value, 1, times some sub-determinant. The determinant of the little submatrix I have left when I eliminate the row and the column of the 1. So I eliminate the column of the 1, I eliminate the row of the 1, I'm left with this guy. Okay? Then I move on to the next component of that first row. I say minus 2 times another little subdeterminant. And I eliminate the column of 2, the row of 2, and I'm left with this guy. And then I say plus the last component of that first row. And then I eliminate the row and column of the last piece. Look at that little subdeterminant. Okay? Yep. Excellent question. I'll get to that at the end. So now I have 3 determinants instead of 1, but the nice thing is they're all 2 by 2. So now I can actually just calculate them. So now I have 1 times 1 minus 0, 0 minus 0, 4 times 0 minus 2. Add those things up, get whatever you're going to get. Okay. The idea is we expanded this thing. Now, once you know that process of expansion, the useful thing is that we don't have to expand along the first row or column. We can expand on any row or column. Right? So what I want to do is pick the row or the column that has the most zeros in it and expand down that row or column. Right? Because that eliminates a lot of my terms. So here, if I expanded across the second row, I would only have one thing to do. I'd have 1 times 1 little subdeterminant. Okay? Now, that negative, where does that come from? Every one of the components in this matrix has an associated sign to it. And a lot of times people just go through and tag them right away like this. You might recall this from linear algebra class, tagging them all. Where does that come from? The more formal definition, the determinant has a leading coefficient that looks like this, where you take -1 and you raise it to the I plus j power, where I and j is the location of that component, right? It essentially just alternates the signs as you go through it. That's where it comes from. Okay. So if I was expanding down this row instead, I would have 0 times some subdeterminant, but I don't care, times 0, plus 1 times subdeterminant, which would be 1, 4, 2, 1, plus 0 times some subdeterminant, which I don't care about. So the nice thing about spanning on that middle row is all that stuff goes away, and I'm left with this little guy. Okay? So that's what you want to do in that homework. One of those columns has 2 zeros in it. If you expand down that column, you basically don't have to do anything because you're just left with factors. Yep. Yes, in fact, you have to. First, you got to subtract lambda on the diagonals. Then you take the determinant using this method. You can't do any row operations because those will screw up your determinant values. It gets a little bit tedious. But one other thing I'll say is this, 2 other things. Let's say you have this thing. I got to calculate this determinant, right? What happens? Well, if I expand on the first column, well, the most zeros, I get 2 minus lambda times some subdeterminant. The subdeterminant, though, looks like this. which is also a diagonal matrix. And then if I calculate that subdeterminant, I get this, 6 minus lambda, 17 minus lambda, minus 0. And then I find the right lambda values, I get 2, 6, and 17, which were the values on the diagonal of my original matrix. So, good stuff. That being said, any questions? Yep. 4 by 4. You're gonna like this one. You do it the same way, exactly the same way. Now I add a bunch of values here. I expand on the row. I get 1 times the subdeterminant. My subdeterminant now looks like this. Minus 2 subdeterminant. And all of those 3 by 3 determinants I have to break down into smaller 2 by 3 determinants. So how do you do a 4 by 4? Use Mathematica. All right. Any questions so far? All right. Goal for today now. Let's get on to our complex and repeated roots idea. We're really just going to focus on complex roots today. Okay. So, once again, like pretty much every other topic that we have talked about in this chapter, we're really just extending what we did with higher order linear differential equations. Okay. So if we look back at what we did when we had x prime plus x prime plus x equals 0, auxiliary equation, found some roots. Well, sometimes we would get roots that look like this. We would get roots that look like 2 plus 3i. Oh no, we have complex roots. Okay. And if you had those complex roots, what was your solution? What did your solution look like with these complex roots? E to the 2t times the quantity cosine of 3t sine of 3t, right? And just like we were talking about auxiliary equations, we just got used to writing that stuff down and kind of forgot where it came from. Same thing here, we got complex roots, and we just said, okay, plug it into my equation and I'm all done. Right? But where did this equation come from? Where does this formula come from? And it comes from this. So I'm going to expand this out real quick. I'm multiplying through by that e to the 2t. And I can see we really have two solutions. There's one solution, and there's the other solution. Now we had our complex roots here. And so really, remember, we assumed our solution was just this thing. And so with that complex roots, our solution really should have just been this. E to the 2 plus 3i times t plus c2e to the 2 minus 3i times t. That's really what our solution should be, right? And that is a solution. The only problem is it has these complex values in it. And that's hard for me to use in real applications. So I need a way to convert this solution into real solutions. Remember, the idea is we needed two linearly independent solutions. They form the basis for our solution space. Is that the only basis? No, there are infinitely many bases. Right? So we don't like this basis, let's just choose a different basis. Right? We can find a whole bunch of solutions here. I can say C1 equal to 3 plus C2 equal to 4, add them together, I have a new solution. And then find some other solution. Maybe that's a good basis, right? I can use any kind of basis I want. So I have solutions that look like this. And what I did was I took one of them and I distributed that t. and I rewrote it like this. And then we used our Euler's identity, which says e to the I theta is equal to cosine of theta plus I sine of theta. Okay? And that's the identity that you need to know, right? That's an important one. That's like Pythag. Right? If you're going into engineering, you need to be able to write that guy out. Okay? It's used all over the place. Okay? Now, when I apply that here, I get e to the 2t, and then I apply that identity to my complex piece. And I get cosine of 3t plus I sine of 3t. And really, if I distribute that e to the t, I get e to the 2t cosine of 3t plus I times e to the 2t sine of 3t. That looks pretty familiar, right? Doesn't that pretty much look just like my solution here? It does. And so the big idea here was that if we use one of our complex roots and we generate this solution that has a real part and an imaginary part, I can really just use the real part as one solution, the imaginary part is the second solution, and then I have two linearly independent solutions. I can just form my general solution from the real and imaginary parts. Okay. Now, why can I do that? Well, if I did the same thing with the other one, 2 minus 3i, I would get the same kind of solution with a minus here. And then I could say C1 plus the first one, C2 the second one. I could choose values of C1 like I over 2 and 1/2. And if I added them together, it would eliminate the sine piece. And if I had some different combination, it would eliminate the cosine piece. And so I could choose my constants just right to get just the real, Okay? But because I know that I can always do that, I can really just grab those pieces. Questions? So really the process should have been plugged into the formula. The process should have been use your complex roots to generate this expression that has a real and imaginary part. Use the real part as one solution, the imaginary part as the other solution. That's the general process. Okay? Questions there? All right. That's the same thing we're going to do with systems. I'm going to look at a system that's going to look like this. I'm going to get an eigenvalue that looks like that. And I'm going to get an eigenvector, which I'm actually going to call z now, because it's going to have complex values, and we use z's for complex values a lot. My z vector is going to look like, who knows, 3 plus I and 2. And I'm going to plug one of these, because this will be like 2 plus, plus or minus. I'm just going to grab one of them, and I'm going to plug them into my assumption that u is equal to z e to the lambda t. I'm going to plug these complex values in. I'm going to get this big ugly mess. And that big ugly mess I'm going to have to rewrite as some stuff plus I times some other stuff. And as soon as I get it into that form, I'm going to use this to be my U1 solution. I'm going to choose that to be my U2 solution, and I'll form my general solution. This is like an outline for the process. I want to give you the outline because each step is tedious, right? Each step is kind of long, and it's easy to get lost along the way. But this is the roadmap. Calculate our eigenvalues, eigenvectors, throw them into here, and then we have to manipulate it to get it to this form. And then we just grab the real piece and grab the imaginary piece. Questions? Everybody ready to dive in? Want to stretch first? All right. Here we go. Go ahead and calculate the eigenvalues. All right, so here we go on our calculations. I wrote A minus lambda I. I'm taking this guy minus -1, that's plus 1. 1 minus 2 lambda plus lambda squared plus 1. Lambda squared minus 2 lambda plus 2. Look to factor it. Doesn't look like I can factor it. So when is this guy equal to 0? Got to use the quadratic formula. I get 2 plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. 2 plus or minus, this is the square root of -4, so that's 2i. Looks like I have 1 plus or minus I. So I have complex eigenvalues. So now I'm going to use the first one, lambda I plus, or 1 plus I, to find my eigenvectors. I'm going to plug it into a minus lambda I times my eigenvector equals 0. Once again, I'm using Zeej because we're kind of dealing with complex stuff now. That's the notation for complex values here. When I plug this in, you got to be careful with signs. This is 1 minus lambda. 1 minus the quantity, 1 plus I. 1, -1, 1 minus the quantity, 1 plus I. Okay. Times Z1, Z2 equals 0, 0. I'll skip that stuff. I'm really row reducing this guy. I'll simplify this a little bit. You get minus I, 1, minus 1, and minus I over here. Now, do I need to row reduce? One of these rows should be multiples of each other. Are they multiples of each other? Do they look like multiples of each other? They don't really look at multiples to me. Sometimes it's really hard to see, but they are multiples of each other. What's the multiplier? Well, to maybe try to manipulate a little bit, what I'm going to do is I'm going to take the first row and I'm going to multiply it by I, the conjugate, the complex conjugate. If I multiply that first row by I, I'll get -I times I. That's -I squared, but I squared is -1. So that would be +1 here when I multiply by I. Over here, I get I. Now I can really see, yes, they are multiples of each other. It's just the multiplier is a complex value. Okay? So even though they didn't look like multiples, they were multiples. You don't have to write that step down because I don't actually need to do that. I just wanted to demonstrate they are multiples. But because they're multiples, if I did the full row reduction, one of them would go away. Right? So I can just grab either one of these rows and write out my equation to generate my eigenvector. I'm just going to grab that first one and say -I times x1 plus x2 is equal to 0. Which means my eigenvector, well, let's see, I can just choose some values here. If x2 was 1, I'm sorry, let's not do that. That'd be hard, right? If x1 was 1, let's do that. That's easier. If x1 is 1, what would x2 have to be? I. That is an eigenvector. There's your eigenvector. I should probably make that z I should probably make these z's, sorry. Because just like before, I'm looking for a value for z1 and z2 that satisfy this equation. I know that if I find one, all the rest are just multiples of this vector. Okay? I grabbed the first equation. Did I have to do that? No, I should have been able to grab this one too. Let's see what happens if I do that. You don't have to write this down. This is just extra, right? If I grab the second row instead, I would have negative x1 minus I times x2 is equal to 0. Maybe I'll just add the x1 to the other side. I'm z's, right? Z's. What is my eigenvector here? Well, if z2 was equal to 1, then z1 would be negative I. Did I get a totally different eigenvector? I didn't. Because if I take this eigenvector and I multiply it by I, if I scale this by something, what do I get? Well, I times negative I is positive 1. I times 1 is I. These eigenvectors are just multiples of each other. They're not different eigenvectors. Okay? It means they're both pretty much the same. It also means that if you wrote down this one, you are correct. If you wrote down this one, you are also correct, making it very fun to grade. Okay, but the idea is your answer could look very different than somebody else's or Mathematica's output and still be correct. Okay, as long as they're multiples of each other. Any questions there? All right, so I got my eigenvector. Yay. Got my eigenvalue eigenvector. So what does that mean? That means my solution should look like 1i e to the 1 plus I times t. Because if you notice that lambda 1, the first eigenvalue was 1 plus I. What was the other eigenvalue? Minus I is the complex conjugate. The same thing is going to be true with the eigenvectors. So if I found one eigenvector to be 1 negative I, or 1i, then the other eigenvector, like that's the first one, the other one associated with the other eigenvalue would be the conjugate. It would be 1 minus I. Remember, when I say conjugate, this is what I mean. If I have this thing, if I have 3 plus 2i, that's some complex number. The conjugate is 3 minus 2i. That's the complex conjugate. Okay? So I don't have to calculate that second eigenvector because I already know what it is. Now, I just grabbed the first eigenvalue eigenvector. I threw it into my solution. There's my solution. And just like in the higher order, my goal now is to transform this thing into something plus I times something. And once I get it into that form, then I know that this is going to be one solution and this will be my other solution. I can just grab the real and imaginary parts. Okay? So we grab the eigenvalues, eigenvectors, we throw them into this assumption. Now we just do the manipulations to get them into this form. Okay? All right. Well, how do we do that? All right, I got 1 and I. I'm going to have e to the t times e to the t times I. I'm going to give you a little head start here. E to the t times I. Now we're going to get Euler's identity on that, right? So that piece is going to turn into cosine of t plus I sine t. Okay? And then I have to multiply the vector like this. See how far you get with the other one. You'll understand it's much better if you start writing this thing down than figure out what's going on. I'll show you when I'm working with these theories. All right. So I just used Euler's identity. That's the one you got to be able to write out. Right? I'm converting e to the ti into its associated form here. That's Euler's identity. And now what? Well, now I just take this scalar stuff times this vector. So I'm going to get a big vector. It's going to look like e to the t cosine of t plus e to the t I sine of t. And the second component is going to look like I times e to the t cosine of t, and then minus 1 e to the t sine of t, right? Because I have I times I. Any questions here? All right, well, I got an I term here, and I got an I term here. I will just switch the order of the addition of the denominator, basically. I'll rewrite this as e to the t cosine of t plus I times e to the t sine of t. And down here, I'm going to write this as negative e to the t sine of t plus I times e to the t cosine of t. And then I'm just going to write it as the sum of two vectors. E to the t cosine of t, negative e to the t sine of t, plus I times e to the t sine of t, e to the t cosine of t. All I did was take my complex eigenvalues and eigenvectors, throw them into my solution form, and then I just converted it into this form. Once I'm in this form, I know that I can just use the real part as one solution. I can just use the complex part as one solution. The complex part is the real vector. It does not include the I that is in front of it. Okay? Any questions about that manipulation? Just a little vector addition stuff. All right. So now my final solution. My final solution is just C1, U1, C2, U2. It's C1 times this stuff, t cosine of t, negative e to the t sine of t, plus C2 e to the t sine of t, e to the t cosine of t. What happens when we look at complex systems? Same thing we've always done. The algebra just gets a little bit trickier, and we have some I's in there we got to be careful about. Vector addition's a little weird, but it's the same idea, right? We're plugging these values in to our assumption, and we're just monkeying around with it. Any questions about that final solution form? Yep. Where does the I go from here down to here? Yeah. That's kind of what you think about it. In some sense, it's actually true because all we're doing is saying that that is one solution, that whole big thing, with the plus I and the other stuff. If I went back and grabbed the other eigenvector and did the same thing to form solution number 2, I would get basically the same expression except a negative sign in there, right? And then I could take some constant times the first one, some constant like this. I could manipulate it to kill off the i's. Right? And so I could do that every time. So basically, I'm going to generate new solutions that are real, and those new solutions will be linearly independent. And I can use them to formulas. Right? So essentially, I'm manipulating the constants to kill the ions. And so we summarize that, yeah, it basically swallows up that. Other questions? Now you have to care about posting the video, right? Because I'm going to call from some mathematicians. It swallows up the eye, really? All right, any other questions? All right, if you get stuck on this and you go to the Learning Center, they're going to say, I don't know what that guy's talking about. That's not how you solve systems with complex values. This is how you solve systems with complex values. You find your alpha and your eigenvector and write your eigenvector as some vector b1, b2, and then you put them into this formula. That's true. We'll get you the same result, right? And it's just a process, it's a memorization of this formula. Formula looks kind of like the other formula for higher order. So it certainly isn't a viable option. It's not a good one, right? You gotta get it down for the exam. You just want to memorize this thing. Do what you gotta do, right? But the real process is important. When we actually use this, it's that idea of putting in combination values, using Euler's identity. Those are stuff you'll see over and over again for large courses. So I encourage you to do that. This is not presented in this text, it's presented in the old text. The old text is not presented in the more general process, but it's a much better process. But I'll leave this up here. If you want to try to interpret it or ask more details about it, you're more welcome to. If you go to the Learning Center and they start talking about the B1 vectors and the B2 vectors, that's what this is. All right. Any questions? All right. Enjoy your Easter.